Okay, thank you. I'm José Diamantino Hernández Guillén. I'm a professor at the University of Extremadura. And in this presentation, I'll explain how a type of malware, in this case, APT, an advanced persistent threat, can use machine learning techniques, in this case, Q-learning, to learn how to spread properly. I'll start with a brief introduction, then I'll explain the mathematical basis of the model and how it is used, and finally I'll explain some countermeasures. I'll start with a brief introduction. First of all, what's an advanced persistent threat? An advanced persistent threat is a type of very stealthy malware directed against one target. In other words, it doesn't seek to spread to as many devices as possible. It seeks to infect one target. This type of malware has increased a lot recently due to the lack. The number of APTs has increased a lot recently because of this type of malware is very dangerous. Early detection of APTs is one of the main challenges that scientific community faces. However, I'm not going to focus on detection. I'm going to focus on countermeasures. As a countermeasure, we can use a combination of honeypots and multi-target defense. Honeypots are used to lure malware, and multi-target defense uses different techniques and mechanisms which change over time. We'll see that the combination of both honeypots and multi-target defense can prevent this type of malware from learning. Next, I'll explain the mathematical basis of the model. This model uses Q-learning theory. This theory considers that at each instant of time, the agent takes an action, U sub t, and receives a reward, R sub t, at the same time that its state can change. To learn and to take good action, this formula is used. This formula is a weighting between the Q values at the current state and at the rewards and Q values at the future state. Mu measures this weight and gamma measures the impact of the future Q values. Next, I'll explain how this kind of malware can use Q-learning, can use this kind of machine learning technique. At each instant of time, the malware is located in one node. For example, in this case, the malware is located in this node, and in this case, the malware is located in this node. Then the state of the malware is different in this network than in this network. The possible actions are the nodes that are the possible actions are the neighbors of the node where the malware is. For example, this node has 3 possible actions, and this node has 1 possible action. Finally, the rewards are good if the malware finds the target node, and the rewards are bad in any other case. Once the malware has learned, it knows the best path to reach the target node. For example, in this case, the malware starts from node 33, and the target node is the node 31, and the orange node represents the best path to reach the target node. In this case, it's the shortest path because there are no countermeasures. Finally, I'll explain some countermeasures against this type of malware. If we use static honeypots, the malware avoids them and learns a longer path, but it still learns. However, if we use a dynamic honeypots moving around the target node, the malware can learn properly. How in this example? In this example, the malware can't reach the node 31. However, in this example, the malware reached the node with a longer path. Finally, I'll explain the conclusion. The conclusion, it can be said that this kind of malware using machine learning techniques can be really dangerous. However, the combination of honeypots and multi-target defense can prevent this type of malware from learning. Thank you for your attention.
Jose, anytime. Anyone has any question? No one? Okay, thanks, Jose.